All right, so we've looked at vowels. Now let's look at consonants. And as when we looked at the acoustic properties of consonants, we're going to have to divide this out separately by different categories, different classes of consonants, because they all have different properties on the perceptual side as well. We'll start with approximants. And now the big thing here is formant transitions, formants and formant transitions. So, for example, between the two glides in English, the y and w, second formant frequency is a big deal. Remember that these are similar to the close front vowel e and the close back vowel u. So going back, remember that the second formant becomes much closer when you're in a back vowel than in a front vowel. And because these approximants are very closely tied, very similar to those vowels, you see a similar formant frequency identity there. The liquids R and L, the R and L, those alveolar approximant, you could say the central and the lateral alveolar approximants in English, uh, the third formant is the real distinguishing factor there. Remember that the R sounds have very low F3 frequency, and that comes through very clearly on the perceptual side as well. Another interesting property here is formant transitions. Now, we've talked about formant transitions as helping to indicate place of articulation, but what we want to see here is the duration of the formant transition. So, for example, if you have these formant transitions where they're really low into the consonant, that tends to indicate a bilabial place of articulation, like b. But if you take longer to come out of that, like that, you hear more of a w sound. And there are actually studies that have done this. They've deliberately varied the time it takes to transition from that point into the steady state of the vowel. And what we find is after a certain point, we'll talk about category boundaries in the next video. After a certain point, the percept transitions from B, from a plosive, to W, to an approximant. So it's kind of interesting, the speed of the amplitude change. The percept of that will be affected by things like speech rate. So there's a lot of interlocking things that come in here, and we'll talk about those again some more in the following video where we talk about theories and trying to capture all these different patterns. All right, that's approximants. What about fricatives? Well, as we learned before, um, with fricatives, uh, the concentration of noise energy is important. So is the energy concentrated high or low? Is it overall high amplitude or low amplitude? Is it overall louder or less loud on the perceptual side? These are things that can help identify fricatives. Duration doesn't seem to be a very helpful cue, although acoustically there are systematic differences in duration between different fricatives. And formant transitions are a factor here. Now, um, one of the things that we have looked at, that phoneticians have looked at in the perception of fricatives, is trying to identify, if we have multiple cues, which ones are more important. And there's this paradigm of mixing the cues, swapping cues out to help get at this. So here's a stylized example of uh, an F, which has slightly lower energy distributed across more of the spectrum in its noise, and then it has labial-like formant transitions, versus an S, which has higher intensity energy concentrated higher, and it has more of an alveolar type of formant transition. Now, what happens if we splice that? We have, say, the noise energy from F and the formant transitions from S. What's perceived there? This sort of approach can be used to help us see which, if any of the cues that we're interested in is dominant in perception. If you splice the energy cue of F and the transition cues for S, and people perceive the F, then you're going to infer that the energy cue is dominant and the transition cue is less important, and vice versa. And of course, it's always a continuum. Each cue is contributing a certain amount. How much is it contributing? Lots of ways to get at that. So that's cross-spliced perceptual stimuli, conflicting cue stimuli, different names for the same thing. I guess cross-splicing means you're actually taking the original sounds and cutting them up and putting them back together. Conflicting cue, you could be doing that. You could be synthesizing them artificially. Okay, so that's a little bit of stuff about the fricatives. Now, nasal consonants. Nasals have a distinctive manner and it comes out in the acoustics. So that's something that can be picked up by hearing the sort of more broad, low energy, wide bandwidth formants characteristic of nasals, that very low frequency nasal murmur and so on. And place of articulation is signaled by the exact placement of the nasal murmur. It can be hard to see the differences in a spectrogram, but there are differences there. And the formant transitions going into and out of the nasal. It's probably also worth pointing out that in normal face-to-face spoken conversation, there are also visual cues. So the nasals are famously, acoustically, they can be quite difficult to tell apart. So if I go mm and mm, you may not be able to tell which nasal I'm making. But if I say mm and you definitely know that first one was bilabial because you can see it. So although we focus mainly on acoustic and auditory stimuli here, visual cues are definitely used by listeners when they're available. All right, let's move on to plosives. And as we've talked about before, formant transitions are important before and after, sort of leading into the consonant and coming out of the consonant. The closure duration varies. Generally, voiced plosives have a shorter closure duration than voiceless plosives, for example. And the concentration of energy in the burst gives information about the place of articulation. Voice onset time, something we can hear. Do we hear voicing carrying on before the release? So that's a positive voice onset time. Uh, sorry, negative voice onset time before. Does voicing start right at the release? Zero voice onset time. Does it start after the release? That's the positive voice onset time. That's aspiration. And what the listener hears depends on a combination of various things. And there's this one famous uh, diagram, famous plot, uh, that really does illustrate how very context dependent these percepts are. For example, the vertical dimension here is where most of the energy is concentrated in the release burst. And along the bottom, we have various vowels following the sound, following the release burst. And depending on which vowel follows the release burst, that energy can, a particular type of particular frequency of energy, say it's concentrated here around 2000 hertz, can be perceived as a P or a K. Uh, and if it's higher, maybe a P, a K, maybe even a T, depending on which vowel is in the context. So this is, first of all, a little troubling for the idea that, you know, it would be nice to have some invariant acoustic um, indicator of what sound we have. And this does not support the idea of invariant acoustic indicators. But it does give us some insight into how people are listening. People are clearly integrating multiple cues into their perceptual system before the brain says, "Aha, I know what sound this is." Right. Um, so I think I'm going to close this video there. It's complicated, right? We can, it's complicated. It's not complicated in an intractable way. We can come up with graphs like this. We can characterize those relationships, but those relationships are not going to turn out to be this straightforward one-to-one correspondence. So there you go. We've looked at approximants, fricatives, nasals, plosives, some of the issues, some of the perceptual patterns that we've been able to identify through research into these. And next video, we're going to look into some theories of speech perception, ways that researchers have tried to put these things together into a model of how that all is going. Why do we see these patterns? What's going on, and listeners' brains that generates those patterns.